I'm very pleased to be here today, have the opportunity to share with you some of our latest developments around power distribution, control systems, and I will take some time to share with you our experience with the UK DNO as a result of having spoken to a number of DNOs in Europe recently, having launched the Smart Grid venture in Hitachi Europe. And I will then plan to conclude with our point of view in the market, looking at the increasing amounts of renewables connected to distribution networks. Let's say very quickly a few words about Hitachi. Apart from being delighted to be the sponsor of this event today, we are a global engineering firm with capabilities in ICT, power, electronics and IT. Our roots, I have to say, are very Japanese. But in 2006, we committed to two major aims. The first, to develop our technology not only for Japan, but also for global markets. Second, was to make sustainable development at the heart of our customer engagements. Our social innovation business is basically grouped around three major pillars of ICT, power systems, and industrial transportation and urban development. And in particular for smart grids, we see the fusion of ICT and power electronics as a key driver for growth, merging with IT and supporting industry and mobility technologies. We've been involved in a number of smart cities and smart grids projects recently. We see a deal of convergence, in particular in the UK, working with Western Power Distribution on a voltage control system based on a number of DSDCs with dynamic control systems, which Mike will explain later today. In Malaga, collaborating with Mitsubishi Heavy Industries and Mitsubishi Corporation, deploying a number of management and charging electric vehicles. In Hawaii, we are in the process of developing a micro DMS to accommodate an autonomous network in a presence of sort of in an island environment. And in the northeast of Japan, in Rokasho, we are working with a wide number of stakeholders, in particular technologies to create a self-sufficient microgrid. I'd like to invite Mike, please, to cover the Western Powers project.
Thanks, Andreas. Okay, well, the next slide, hopefully. Good. I spoke to one or two DNOs this morning, and unfortunately they gave my presentation back to me, which was interesting. I'm going to start, first of all, with this slide. And it profiles a couple of the, well, one of the core issues for DNOs everywhere. This is not just in the UK, but in mainland Europe. That's a voltage control on high voltage and low voltage networks. One of the problems on rural networks, and you really need to split it out into rural and urban networks. No point in talking about networks in general. In the case of rural networks, and if you're talking about, for example, 11 kV networks, the major cause of let's call it voltage variation is wind. There's going to be a bit of PV, but what we're seeing at the moment is that we have a number of wind developers, and it's a simple matter of fact. If they put, for example, a megawatt of wind on an 11 kV line, it's going to cause considerable voltage variation. You've got high wind output, low demand, you're going to get, well, high volts. And you're going to get the reverse when you've got low wind output and high demand. In the case of urban networks, we've got PV is coming along. You're going to get clustering of PV. In the case of the UK, of course, if it's, let's say, in June, something like that, everybody's at work, it's midweek, it's a sunny day, the kids are at school. You've not got much demand on the LV network. So, again, you're going to see quite high volts. The DNO's get out of jail free card at the moment is that PV is going to cut off when the volts get too high. That's not sustainable for the future. And of course in winter we've got the problem of what about ground source heat pumps, air source heat pumps, and probably after 2015 when electric vehicles comes along, how are you going to get enough power into the network to sustain these things, to keep them powered up? This chart gives you an idea of what happens when you've got some wind connected to an 11 kV line. The point on the far left is the primary substation. The top two dark blue lines are outputs from a small wind turbine group that is, I should explain, this bit here is distance from the substation. So the x-axis just charts out distance from the substation. The y-axis is simply 11 kV volts. The dark blue lines show relatively high outputs from the wind turbine. And you can see in a heavy load situation, well, the high output kind of keeps the line reasonably straight. When you've got low output, which is the two lower lines, well, you can see the volts are dropping all the way along the line. These volts are just about within statutory limits when you start looking at LV volts, just about. Surprisingly, or perhaps not surprisingly, if you look at light load situation, what you see, of course, is when you've got high energy from the wind turbine, or a lot of power out from the wind turbine, it's going to push the volts up. If you've got low output from the wind turbine, well, the volts stay kind of level-ish. If I move on to the urban networks, we've got two pretty interesting problems. One is voltage spikes on 11 kV networks, or MV networks if you want to call them that, when you've got cluster PV and you've got the cloud over the sun. In the case of ground source heat pumps, you've got a rather different problem. And the Dutch discovered this, and they've got a solution to it. But basically, just imagine you've got, I don't know, say 100 houses. They've all got ground source heat pumps. And you lose power for 4 or 5 hours. This can happen. I was off for 8 hours last week because of the change in the substation where I live. But anyway, the point is that when the power comes back on, all those ground source heat pumps are all going to start at the same time. So it's then a bit of a toss-up whether your cable goes or your transformer blows up. What the Dutch have done is to actually have remote control on the ground source heat pumps. That's not an option. That's a requirement if you still want to have a network left. This slide shows, actually it's a slide from Japan. It shows a city that's got large quantities of PV. It's not come out terribly well, but just about every roof you can see there has got a panel on it. Now, I mentioned the issue of voltage spikes. This is not some kind of theoretical construct. If you look at the black line, over on the far left, you can see it's just a little bit above the 6,600 or 6.6 kV point. That's nominal, well, HV or MV volts in Japan. If you go along that black line, suddenly you can see it drop down. That's when you get a cloud or a couple of clouds going over the sun. Suddenly, instead of all the panels producing power that is consumed locally, suddenly they're not. Suddenly the local transformer's got to produce the power. Suddenly you get a big drop in volts. And of course, the reverse is going to happen when the cloud disappears. You're going to get a positive voltage spike instead of a negative voltage spike. And this really happens. This is an example from Japan. When we speak to the DNOs, obviously they're looking for solutions. However, they've set some conditions to the solutions that they're looking for, and I've listed 3 of them here. Please keep these in mind as I proceed through. Right, we'll miss that one. Andreas mentioned the project we've got with Western Power. The bottom part shows 2 substations, one at each end, they're both primary subs. There's a network open point because in rural networks you normally have an open point. Well, in urban networks you have an open point unless you run a mesh network. You've got a wind farm not far from the network open point, and the first part of our project is to install a D-STATCOM reasonably close to the wind farm. Good. This slide provides a few more details on the project. It's in 2 parts. The first part of the project is to simply prove that the D-STATCOM will regulate HV volts, and by implication, it will regulate LV volts. The second part is to install 3 StatComs on a network probably in South Wales, and it's going to include a thing called a voltage quality controller. That will communicate with the StatComs, it will control them to a certain extent. It will also control the online tap changes in the primary subs. And it will also control, if you happen to have them, some auto transformers, which are basically electromechanical devices that some DNOs use to try and regulate line voltages on the 11 kV network. So, right at the moment, we're hoping to have delivery of the StatCom, I hope, next month, or maybe in early August. And I would say we're going to have some sensible results from the trial by October or November. You're probably asking, does it really work? Well, look at this slide and then just look at that one. Right. It's got the same y-axis. So that's light load there. And then if we flick forward, you can see... oh, that's good. Yes. You can see that the lines are now much closer. We've done a simulation, and we believe that the StatCom will reduce voltage variation by about 66%, which is interesting. What it means is that in this particular line, if somebody else came along to Western Power and said, hey, we'd like to install some more wind turbines, actually you could do that. So one aspect of the StatCom is it lets you install more renewables on rural networks. We think it will do a few more things on urban networks, come to that. Let me just pop past that one. If you're wondering what it looks like, there's a photograph up there. It's about 2 meters tall, 1.5 meters across, and about 1 meter thick. Although there's a picture of it sitting on poles, normally it sits on a slab of concrete. There's a line diagram, a rather crude one, over on the left-hand side. This is a shunt-connected device, self-evidently. What's interesting is it's extremely fast. It can react to voltage variation in about 40 milliseconds. That's very roughly 2 wavelengths, so this is a really fast device. We've got it compensating for wind at the moment. We're pretty confident that it can compensate for PV, because in fact the thing was designed to do that in the first place. I think I'm just about on time now. This is, to be honest, this isn't our vision, although it says it's actually all over it. This is the vision that we've got from speaking to DNOs. So, it's not us just saying this. This is what some of the DNOs we speak to say. And in rural networks, you can see now we're going to start with the StatCom. Next year, we're going to include the VQC. We hope to connect storage to the StatCom. I should maybe hop back. You can see a thing called a DC capacitor there. That's part of the StatCom. In fact, it's entirely possible to bolt on some storage next to the capacitor, and then basically you've got a storage system as well. And that's how we see rural networks. In the case of urban networks, we're talking to some DNOs. A lot of interest in putting small StatComs on the LV network. The issue is developing a small StatCom. Our hope is to scale this thing for LV feeders in the future. And there is also a micro DMS under development, which would communicate with assets on the LV network, and perhaps also communicate with things such as home energy management systems, which the chap from Alertly mentioned. And, well, that's what we're hoping to do in the future. And now, I'm just over time a little bit. I'm going to pass back to Andreas.
To date in Europe, even though many member states have developed renewables, most have been sort of large point sources, generation, connected transmission lines. Maybe a large-scale exception is Germany with photovoltaics, which for the most part has been connected to low voltage. Integration into power networks has, for the most part, required modifications to grid codes. We believe, however, that there will be significant expenditure in network equipment, and as a result of sort of not engaging in long-term processes of putting more copper on network lines, which is not a sustainable option in the long run. So we expect to see strong growth of distributed generation, with a focus on rural wind and urban PV, in particular, given the introduction of feed-in tariffs, as well as some relaxation in planning rules. Voltage issues in low voltage networks, 11 kV, 33 kV networks as well. And we hope and we expect LCM projects to bring some findings and answers to these issues in the near future. So in the meantime, we'll continue to engage with LCM projects, smart cities projects at the European Commission level, leveraging our experience from Japan, supported by NATO. Essentially, so as to conclude, it's very simple. Our idea is we will gear our growth to meeting the requirements of our customers, seeing DNOs as a target segment, and potentially renewables. And we believe this is a quite unifying goal and very exciting market to operate, bringing innovation and new commercial arrangements. Thank you very much.
Thank you.